This demo presents an explainable continual learning pipeline for digital twin-assisted ORAN control. I begin by running the main controller script. In this demo, the main controller is an xApp that runs a PPO reinforcement learning policy. This first terminal starts the simulated multi-cell radio access network digital twin together with a PPO-based xApp controller. The environment continuously generates live network measurements, including SINR, outage ratio, head-of-line delay, throughput, queue ratio, and drop traffic. Based on these observations, the controller selects two types of actions: a continuous power scaling action and a discrete control mode. Next, I open the live dashboard. This dashboard provides a real-time view of the control loop. At the top, we can see the current network performance, including throughput, average head-of-line delay, outage ratio, average SINR, queue ratio, and dropped bits. Below that, the dashboard shows the selected control action, including the mean power scale and the current B mode. The plots then show how the controller behavior changes over time, including the distribution of selected control modes. The third terminal starts the continual LMUT explainer. This module watches the live rollout log produced by the controller. As new data arrives, it updates the interpretable model and learns an approximation of the controller's behavior. The important point is that this explanation layer is not static. It is updated continually while the control loop is running. Returning to the dashboard, we can now see the interpretable decision rules. These rules explain the controller's behavior in a readable if-then format. One set of rules explains the power scaling action, and another set explains the selected B mode. The next terminal runs the logger harmonizer. This component combines the live rollout CSV and the dashboard status JSON into a structured event stream. Each event contains the timestamp, current network KPI values, selected action, and explanation information. This makes the experiment easier to inspect and audit after it has been generated. I then start the query server. The server runs locally and exposes the harmonized event stream through a fast API interface. In the browser, the Swagger interface shows the available query endpoints. These allow us to check the system health, retrieve a run summary, jump to a specific time, analyze interval statistics, find mode changes, explain changes, and retrieve the top rules at a selected time. This turns the live experiment into a queryable and inspectable record of controller behavior. Finally, I open the LMUT Decision Tree Activation Path Visualizer. Here, a selected event is passed into the trained explanation model. The visualizer shows the state vector, the ensemble prediction, and the exact path followed inside the decision tree. The highlighted nodes show which conditions were activated, and the final rule explains how the selected control decision was reached. The key takeaways are threefold. First, the demo shows live reinforcement learning-based control in a simulated multi-cell RAN digital twin. Second, it shows continual explainability, where the LMUT model keeps learning explanations while the system is running. Third, it provides auditable decision-making, because an individual decision can be traced through an interactive decision tree path. Overall, this demo shows a complete local pipeline for explainable digital twin-assisted ORAN control.